Thanks. Very welcome to my presentation. This presentation about the establishing of electron equilibrium in TLD using NCNPX Monte Carlo code. The title of this presentation is Investigation of Conditions for Electron Equilibrium Establishing in Thermoluminescent Dosimeter. Thermoluminescent dosimeters or TLDs are the best instruments to measure the dose and are widely used for radiation detection in the fields of environmental, medical, industrial, and personal applications. TLDs can be used for the absorbed dose measurements performed with the aim to investigate cases where dose prediction is difficult and not as a part of a routine verification procedure. For example, measurement absorbed and effective doses in the human body. Due to the reliance of Monte Carlo code to do dosimetry calculations, nowadays TLDs have been also entered into these codes. By using Monte Carlo code and also anthropomorphic phantoms, phantoms are three-dimensional modeling of human body. Using Monte Carlo code and phantoms and then to do dosimetry calculations can be estimated the dose even before persons are placed in specific situations. This is a voxel phantom. The basic point for employing a Monte Carlo code is their ability to provide the accurate estimations within tolerable runtime. Some advantage of TLDs in measurements such as small size, mostly 3 by 3 by 0.89 cubic millimeter, are problematic in Monte Carlo simulation because in this case simulations are extremely time consuming in order to achieve a reasonable statistical accuracy. One way to reduce the runtime is to establish the electron equilibrium. In this study, we used NCNPX Monte Carlo code. Therefore, if the electron equilibrium to be established, we can use the Karimi approximations instead of the absorbed dose calculation in the NCNPX code. For calculate the Karimi approximation, we use F6 or star 4 tallies, and for calculate to absorb dose, we should use star F8 or plus F6 tallies. LIFTLD was modeled in NCNPX code and photon energy of 0.08 and 0.3 and 1 MeV were considered in this study. What's the meaning of the electron equilibrium? If the number of electron enters into the cell to be equal with the number of electrons emerge from it, the electron equilibrium is established. How to establish the electron equilibrium in simulation of TLD by NCNPX Monte Carlo? We consider three ways in this study. One, area of TLD is surrounded by the different wrapping materials. Two, placing a huge volume in the front of LIFTLD. 3. Enlarging the TLD volume and replacing LIF by air as a TLD materials. The first way, LIFTLD is surrounded by the different wrapping materials such as aluminum, polyethylene, Teflon, PMMA. The thickness and volume of this wrapping were obtained and indicated in this table. For example, in a 1 mega electron volt. The thickness is obtained 0.549, while for Teflon 0.339, and the volume for polyethylene 0.351, and for Teflon is 0.270. Obtained volumes for the TLD valve from various materials explainable by mass energy attenuation coefficients, whereas these coefficients for Teflon are greater than polyethylene, PMMA, and aluminum. Therefore, the required volume of Teflon for the electron equilibrium creation in the TLD is smaller than other materials. Finding suitable thickness and volume for different materials at each energy is a time-consuming process in this method. The second way, placing a huge volume in the front of TLD. Male ICRP reference voxel phantom was used. The male phantom is 176 centimeter in height and 70-30 kilogram in weight, and the specific voxel resolutions. These figures are coronal, sagittal, and transversal view of this phantom. Coronal, sagittal, and transversal. One LIF TLD was placed on the chest and the other TLD on the back of phantom. The response of these TLDs was drawn to 25 photon energy, ranging from 0.01 to 10 mega electron volt into one TLD and other. This phantom irradiated to irradiation geometry, anterior, posterior, and posterior anterior. We select two irradiation geometry. If phantom irradiated from AP, this figure is a response of TLD versus energy, photon energy. If phantom irradiated from AP, this figure for AP and this figure for PA. If phantom irradiated from AP for the back TLD, that body is placed in front of it, and also for the front TLD in PA is the front TLD in PA and is the back TLD for AP. The electron equilibrium established. As seen in figures, when the electron equilibrium is established, the result from F6 and plus F6 tallies are matched together. In photon energy above 500 kilometers, 500 kilo electron volt, the estimated absorbed dose by plus F6 tally is decreased when TLDs are directly exposed from photons such as from TLD in AP. This front TLD in AP and back TLD in PA. You can see the reason of this difference in this figure. In F6 study, in the thermo approximations, electrons are absorbed at the production origin, aren't transported, but in plus F6 study, the electrons transported When the energy increases, the range of electron also increases. Therefore, it deposited some its energy out of cell. When phantom was irradiated from the front, the electron equilibrium is established for back TLD and vice versa in this method. The third way, enlarging the TLD volume and replacing LIF by air as a TLD material. The star F4 was used to obtain a track length estimate of photon energy fluence in the cell. Result of this tally should be gathered with the dose factor to calculate the curve. The figure exhibits the result of a star for tally for air and LIF TLD. The red is the LIF TLD and the black is the air TLD. The result of these have been converted with mass energy absorption coefficient of LIF in different volumes of the TLD for energy of 0.08 and 0.3 and 1 and 10 mega electron volt for energy. The initial volume of TLD was selected to be 0.004 cube centimeter and was decreased about 1,000 times rather than the initial volume. It is observable in figure that very good agreement is seen between results of air and LIF TLDs in very small volume for all energy. For all energy, the response of air TLD and LIF TLD is matched. But by increasing volume, the absorbed dose obtained from the LIF TLD is reduced. Is LIF TLD response. However, the acquired dose using air TLD remains constant. Therefore, when the huge volume is applied, absorbed doses can be estimated precisely by air TLD, which have been made from the huge volume. Then started for and mass energy absorption coefficient of the desired materials in the real TLD must be applied as the NCMP's output. To conclude, in the first method, finding suitable thickness and volume for different materials at each energy is a time-consuming process. In the second method, the establishing of the electron equilibrium is dependent on the position of TLD. For example, if the phantom is irradiated from AP, the electron equilibrium is established just for back TLD. In the third method, the electron equilibrium is established without any restriction, and subsequently simulation runtime decreases. Therefore, this method is the best. Thank you for your attention.
Thank you also. Any questions? Any comments?
Somewhere you have a curve for the variation of the absorption as a function of energy. Is this a photon energy or the total irradiation energy?
Photon energy.
Photon energy.
Photon.
Okay.
Initial photon energy.
Then, if there is no other question,
we thank again to the speaker and pass to the following